Section 6.2. Now here's a theorem for complex conjugate. Eigenvalues of a real matrix. Okay, so A is real. So remember, when you do the characteristic polynomial of A, you're going to get some, lambda to the n, plus, well, a trace, but we'll just say, an minus 1, lambda to the n minus 1, plus plus a0. And from our complex chapter, we know that this is going to factor. Okay, so this factors into linear and irreducible quadratic terms. Okay, so the irreducible quadratic terms, you're going to get roots of a given lambda could equal some real part plus or minus b times I. Okay, so you're going to get roots like that, complex conjugates from those irreducible quadratics. And so, what about the eigenvectors? And so this is the theorem, is that if A is real and has eigenvalue lambda equal, let's say, A minus, or well, we'll go with plus bi, and corresponding eigenvector and I'll use a z. Now here's the hard part, is that z has a line over it like a complement or a conjugate, but it's the vector z. Okay, so eigenvector z. Then A has eigenvalue lambda equal A minus bi and corresponding eigenvector z, and what we'll do, I guess, is we'll put parentheses around that and put a bar over it like that. That's z conjugate. Okay, the key here is that A is real, right? Because, okay, so, looking at this proof, let's try that. So we have, A times lambda is equal to lambda z. Okay, well, A times lambda, A times z, is equal to lambda z. And so on the left-hand side, we've got, a times the real part of z plus I times a times the imaginary part of z. And on the right-hand side, we have lambda, which is a plus bi. And now that I think about it, it'll probably be easier to write z as the real part x plus I y, like that. And so let me use that notation here. So we get ax plus I ay. And so here we'll have the a plus bi times x plus iy. Okay, left-hand side, we've got that, but the right-hand side, if I multiply that out, I'll get ax, and I'll get a minus by, and then plus I times, we'll get an ay and a plus bx. And so that means, because a is real, this is the real part here, that's the imaginary part there, and they have to match up. So ax equals a x bar minus y, not bar, sorry, x, yeah, uppercase A times x is equal to little a x minus b y, and ay is equal to ay plus bx. Okay, now so if we take a times the complement of z, then that is the same thing as a times x minus iy, and so that's ax minus iay. Okay, so there's the left complement there, and then if we take our lambda conjugate times z conjugate, that we get the a minus ib, or bi. I think I was doing bi's, right? Yeah. Let me keep it that way. And then times x minus iy. Okay, and as opposed to the x plus iy. See, so that part there is the conjugate stuff. And so this, again, putting everything together, we get ax minus and a minus make a plus, and then two i's, I squared makes a minus, and so we get minus by, and then plus I times, well, actually probably want minus, minus I times, let's see, we have our bx again. What order did I do those in up here? I did the ay and then the bx. So this is ay and plus bx. And so now here, right, I can substitute in AX. So that's AX. And then here, I can substitute in AY. So this is minus IAY. But that is A times X minus IY. And so that is A times the complement of Z. And so there's our proof, because you see we have, I can rewrite this the other direction, so Z conjugate equals lambda conjugate Z conjugate. So this fits our definition of eigenvalue eigenvector pair, and so that is our proof. Okay, so when we get these for a real matrix, again, this is just for a real matrix, if we end up with this eigenvector pair, then the eigenvalues that go with those are just complex conjugates of each other. And let's see, I think I have an example of this. Let's see, I just need to find what I did with it. I had it right. Oh, here we go. Okay. So suppose A is equal to the matrix 4, minus 2, 1, 2. Then if I want its eigenvalues, I've got 4 minus lambda, 1, negative 2, and 2 minus lambda. And that determinant then is lambda minus 4 times lambda minus 2, and then plus 2. So that's lambda squared minus 6 lambda plus 8 plus 2. That's equal to lambda squared minus 6 lambda plus 10, and I want to set that equal to 0. So I get that lambda is equal to 6 plus or minus the square root of 36 minus 4 times 10, all divided by 2. And so that's 3 plus or minus the square root of negative 4 over 2. Well, I can pull out the 4 out of the square root. So I get 3 plus or minus 2 times the square root of negative 1 divided by 2. And so my eigenvalues are lambda 1 equal 3 minus I, and lambda 2 equal 3 plus I. So now, though, if I look at those eigenvectors, okay, so we'll look at lambda 1 here, equal 3 minus I. Well, so our matrix was 4, negative 2, 1, and 2. So I have 4 minus 3 minus I, negative 2, 1, and 2 minus 3 minus I. And we'll augment that with 0, 0. So just doing the subtractions, we get 1 minus I and a negative 2 and a 1 and a, what is that, a minus 1 plus I in zeros. I'll swap the two rows. So 1, negative 1 plus I, 0, 0, 1 minus I, and negative 2. Okay, now if I take -1 plus I times the top row, add it to that next row, I definitely get 0 in that first spot, so I have this. Okay, so I know I get, well, yeah, so I get 0. Now, that was a -2. Now, I need to multiply the -1 plus I times, oh, okay, well, I did a mistake somewhere. Plus I, right here. I needed a plus I, and so that's a plus I, and so I want a the negative of 1 plus I, so -1 minus I. Sorry about that. Again, I multiply that through. I know I get 0 here, but here, notice these are complex conjugates here and here. So when I multiply those, I will get the magnitude of this thing squared. So I'll get -1 times -1, which is 1. And I'll get, for the y part, I'll get a 1 also. And so I will indeed here end up with 2 minus 2, which is 0, which is what I need. And so my eigenvalue here is z 1 is equal to, well, if I just do the trick of use a 1 here and the negative of this thing here, that would be 1 minus I, right? If I multiply those two together, I will get 0. And so if I let the first component be 1 minus I, and the second component minus I, yep, okay, and the second component be 1, there's my z1. Now, similarly, we'll go with our lambda 2, which was 3 plus I believe, right? 3 minus I, 3 plus I. And so we have, for our matrix, 4 minus, I'll try to do it correctly this time, a -2 there, a 1 there, and a 2 minus 3 plus I, 0 and 0. Again, just simplifying, I do get a 1 minus I. Get my negatives right this time, 1, and I get a -1 minus I, 0 and 0, and once again, you know, I'll swap those two rows, so 1 minus I, 0, 1 minus I, -2 and 0. And I need to multiply this top row by -1 plus I. But again, notice complex conjugates. And so when I multiply through by that, add to the bottom row, I do get, well, these are the same. -1 minus I, 0, 0. I'll get 0 there, and once again, I'll get a 2 minus 2, which is equal to 0. And so, I'll write it here. Z2 is, again, I'll do the little trick. I'll do a 1 plus I here and a 1 there for those values. So 1 plus I and 1. And so Z1 was 1 minus I, Z2 is 1 plus I, and so we see that Z1 is equal to the conjugate of Z2. Okay, so indeed, those are conjugate pairs. So that's a pretty nifty result, that all I have to do is get the eigenvector for one of the two conjugate pairs, and then I know the other one. I just take its conjugate. Okay, so that's a theorem that is not in the text, but I think that's a kind of a cool theorem, so I wanted us to see that. So this complex conjugate idea and with the eigenvectors. Okay, so that's our theorem.